All right, we are at section 28.4, magnetic force acting on a current carrying conductor. So we know that if a charge is on in a magnetic field, a moving charge in a magnetic field, it'll be uh, displaced by the right hand rule. If it's a positive charge, you put your fingers in the magnetic field. The velocity is in the uh, uh, is it the direction of your thumb. Then for a positive particle, the force is out of the palm of your hand, and a negative charge, the force is out of the back of your hand. So now we can extend that if we have current, which is charges in a wire, we're going to have the same effect. So let's share the PowerPoint, and we're looking here. Magnetic force acting on a current carrying conductor. Let's read the little boxes here. You can see there's a magnet, and there's a wire. It's carrying current. The first one, there is no current. When there is no current in the wire remains vertical. There's no movement. When the current is upward, the wire deflects to the left. Why? Okay, look at the arrows in the computer screen. They're all going into the computer screen. So from my perspective, they're all going this way. The current is going up, so that the current we consider positive charges is to the left. Now let's run the current in the other direction, and when the current is downward, the wire deflects to the right. And sure enough, there's the magnetic field, there's the current, and so the force is that direction. Oops, I dropped my pen, or my Apple Pencil, sorry about that. So we know it happens on a single charge. Well, when you have a collection of charges in a current, you get the same effect. So let's advance to the next. It shows a blow up here of a wire carrying a positive charge. The average magnetic force exerted on the charge moving in the wire is Q VD cross B, where VD is the drift velocity. We discussed the drift velocity previously. So the magnetic force on the wire segment of length L is IL cross B. Well, how do we get there? We start with a single charge Q times the drift velocity crossed with B, the magnetic field. Well, this volume of length L times the cross area A, that volume is AL, and so the number of charges in that segment is NAL. So the number of charges times the volume, the number of charges per unit volume times that volume, will give you the total number of charges in the segment. So recall that the current is equal to the number of charges times the charge times the drift velocity times the area. So we have Q VD NA in that equation. So the force is equal to Q V drift times across the magnetic field times NAL. That's how many charges we have. So the force is equal to IL cross B, where L is a vector that represents the length of the wire and is pointing in the direction of the wire. Now that only applies to a very straight wire. Now, what if we have a wire that's just kind of going in all sorts of directions? I mean, you can imagine a wire here. This is just my charging cord, but if you have a wire, you can't determine the force on it because it's going in all sorts of directions. So the magnetic force on any segment DS is I DS cross B, and is directed out of the page in this this particular example. You can see that the magnetic field is in this direction. The velocity is this way, And so it's coming towards me out of the page. So the DF, the varying force is equal to IDS cross B. So the magnetic force on a current is I times the integral of A to B of DS cross B. Okay, now let's do a little quick quiz. And a wire carries current in the plane of this screen toward the top of the screen. So it's going that way. The wire experiences a magnetic force toward the right edge of the screen. In this direction of the magnetic field is the direction of the magnetic field causing this force in the plane of the screen and toward the left edge, in the plane of the screen toward the bottom edge, or out of the screen or into the screen. So let's do it again. A wire carries current in the plane of the screen towards the top. So there's the velocity. The magnetic force is to the right edge of the string, right edge of the screen. So let's see, the current is toward the top. The magnetic force, the magnetic force is towards the right. Which way is the field? Okay, so here's the velocity, here's the force. So the magnetic field is out of the screen. And sure enough, there it is, out of the screen. So the current is up, the force is this direction, so got to contort a little bit. The magnetic field is coming out of the screen. Okay, and that's it for this section. That was section 28.4. Next, we'll do 28.5.